Hey everyone, welcome to our final lecture, which is going to be a little bit about the cosmos and mostly about if there is life. Space! So, where was the Big Bang? I'm sure everybody's like, oh, the Big Bang started at this teeny tiny thing. No, the Big Bang was everywhere. The whole universe at once was a single point. No matter where in the universe we are, we will measure the same relation between recessional velocity and distance with the same Hubble constant. Okay, and the Hubble constant, we're not going to talk about in this class because this is an intro to astronomy, or neither are you astronomy majors. But the Hubble constant is this measurement that always occurs, and that hence it is a constant in equations about space. The expansion of the universe can be demonstrated in two directions. So imagine a balloon, like what we have right here, a balloon with coins stuck to it, and you're going to blow it up, right? So as it blows up, the coins move farther and farther away, and distance creates between them, but there's no center of expansion. Every point on the balloon is expanding the same way. It looks exactly the same as any other. So if we were one of those coins, we would see every other coin moving away from us, no matter which one we were. And so that's how the expansion of the universe is perceived by cosmologists at this point, is that there was no actual central point. We're kind of like one giant balloon that's just expanding. So the same analogy can explain the cosmological redshift that we see. So redshift is the reason that stars essentially appear redder in the night sky. And by redder, we mean that they aren't showing on the bluer end of the spectra. So remember, we see in the visible spectra, and the visible spectra is this teeny tiny little piece of the entire spectra. And it goes from gamma radiation, which is extremely blue, all the way to radio waves, which is extremely red. And so redshifting is when the light given off, or the energy given off by a star, goes from being extremely blue to possibly being more redder. And it's known as the Doppler shift. But redshift isn't actually due to the Doppler shift, but to the expansion of the universe as a photon moves through it. So basically, what it means is that if the balloon's expanding as the photon's traveling, it's almost as if this photon's been staying in the same space the entire time. It's just going, I need to get there. And it's kind of running out of energy. So it's more like the wavelength itself is being stretched as the expansion is occurring while it's traveling. So this means it's not due to its velocity, but rather the changing size of the universe. And we can reverse engineer this to actually determine the amount of expansion that occurred since the light was emitted by its host star. So again, redshift, we like to look at it as, here's the entire spectrum. Here's radio, here's gamma, okay? Here's the visible. And we're going to get things like microwave and X-ray and infrared over here. We get the idea, right? And so the idea of redshift is like the Doppler effect, where it goes this way or it goes this way. So this is blue shift, this is red shift. Okay, so if it becomes bluer, that means it's getting shrunk. And if it's getting redder, it means the wavelength's expanding. So like gamma has really short wavelengths, and as you get farther down, you get that. So what we're experiencing in space is a couple reasons that redshift occurs, or the Doppler effect occurs, that we know of. But this is the overall explanation. Some of it has to do with something we called a window effect, where the light's traveling through dust particles, and the dust particles are blocking out the blue light and only allowing the red light, and so that's a part of redshift. But in this case, we're saying the Doppler shift isn't an actual explanation of the universe as a photon moves through it. That a photon will experience redshift specifically because it's moving, the universe is expanding, which is causing a stretching of the wavelength. What happens to the universe? It had this big bang, it's existing, now what? Will it just expand forever? And this is a question amongst cosmologists and ever since Hubble's constant was found. And it led to two major ideas. One, it will expand forever. Number two, universe collapses back in on itself and we have another Big Bang. So the expanding forever one is kind of depressing in itself because it means that we'll just expand until we're too far apart from each other and we'll kind of just die in the dark alone. So our nearest star will be super duper far away. And I don't mean our sun, I mean our nearest neighbor. So we'll be kind of alone in a cold wasteland of space. Doesn't sound so great. But neither does the universe collapsing in on itself. Either way, probably not going to happen in our lifetime. That's like 5 generations plus away from now. I don't guarantee this, I'm just assuming. So what affects this? What are the ways that we see this choice being made? And it's actually based on density. The idea is how they work. Okay, so consider a rocket ship. When we launch, based on Newtonian physics, two things can happen. It can make it all the way into space, and everybody's like, yay, we made it to space. Or it could fail to reach the escape velocity of the planet and fall back in and go explode. Everyone dies. So this can also happen to the universe. In theory, it will expand forever. We'll move farther and farther and farther from each other, and galaxies will expand. Or it'll expand only to a point, and then it'll slingshot back in like a rubber band. The mass or the density of the universe is what's going to determine everything, because the mass of the planet is what determines the escape velocity. So the density of the and mass of the universe is what's going to determine if it will expand forever or collapse. When we think about this, the denser the planet, the higher the escape velocity. Or the more mass the planet has, the higher the escape velocity. So that means it should be the same for the universe. The more massive or the more dense it is, the higher the chance of a collapse. So if it was a low density universe, everything would keep expanding forever. So the dividing line here is what's called the critical density, which is the density corresponding to a universe in which gravity alone would be just sufficient to halt present expansion. And based on that, with the Hubble's constant of 70 kilometers per megapascal, the critical density is 9 times 10 to the 27th kilograms per meters cubed, which is relatively low. Recent studies show that gravity may not be the only factor influencing these two options. So here's what we're seeing is if we have this low density universe, we essentially go forever. A high density universe, we kind of... So the shape of the universe is one of the factors that will help determine the options for the future, or the fate of the universe. Closed universe, which is a high density universe where space is curved to the point where it does bend back on itself, kind of like a circle, and it closes off. So it essentially does this. So it's kind of like a bubble. With this closed universe, it forms a sphere. The unique attribute of this is that light will eventually return to its point of origin, but from the opposite direction, which is kind of neat. As far as I can tell, it has not happened yet, so who knows how big this sphere is if we are a closed system. If the density of the universe is below the critical value, the curvature of the space will curve like a saddle, and it will have a negative curvature, curving up in one direction and down in the other, kind of like how a saddle does this. This is called the open universe. There we go. So the low density saddle curved universe is infinite in extent and is known as the open universe. Okay. So we've got closed and we've got open. The open universe will expand forever, okay, because the density is below critical value, leading to the saddle shape. But we have this intermediate case. And the intermediate case is if the universe has a density equal to the critical density. There is no curvature and it's essentially flat. This essentially is the space that Newton would have known. It creates an infinite flat universe, which is cool. The shape is what? The answer to which future will occur lies in the density of the universe. Measurements of luminous matter suggest that the actual density is only a few % of the critical density. So for now, it seems we have that saddle shape. But we know there must be large amounts of dark matter matter we can't observe but know has gravitational influence on the universe. So the best estimates for the amount of dark matter needed to bind galaxies in clusters, which means you have multiple galaxies stuck together in a group, and they together move in a direction. And to explain gravitational lensing, which is how light moves around an object, only bring the observed density to about 0.3 times the critical density, which is still below. So we've been monitoring the behavior of distant galaxies since this, whole thing has been going on. So type 1 supernova, also known as standard candles, are great for measuring the behavior of distant galaxies because we can figure out their exact brightness, like how their exact luminosity, which is how much energy they're giving off. So if the expansion of the universe is decelerating, as it would if gravity were the only force acting, then the farthest galaxies would have a more rapid recessional speed. In the past will appear as though they were receding faster than Hubble's law would predict. And receding, I mean coming back. Okay. Basically, it would appear to be slowing way faster than we thought. However, recent data to try to clarify what this would look like found something interesting in that it has actually sped up. Instead of getting red shifts, we're getting blue shifts. These observations indicate that gravity is not the only factor determining acceleration and deceleration. So the question has become, what is? And that's where we get dark energy. Okay, so it sounds like a B-rated horror movie, but it's not. Cosmologists don't actually know what is causing the acceleration of our universe. Although whatever it is carries energy and it exerts an overall repulsive effect on the universe, making empty space expand. It's simply known as dark energy, and it is a huge subject of research today by astronomers and cosmologists. The leading candidate for dark matter or dark energy is additional vacuum pressure force associated with empty space, which is effective only on very large scales and is known as the cosmological constant. So this has gone in and out of favor since its invention by Einstein. So while models including the cosmological constant can fit the observational data, astronomers still don't really know what it means. It's neither required or explained by the known laws of physics. So all we know is that it's comparable to the attractive force of gravity. But the age of the universe depends on its composition. So we currently know its present size, but in order to extrapolate backwards to 0, we need to know how it got to its size now. Previously, we calculated the age to be about 14 billion years. But recent knowledge of dark energy means it may have expanded faster in previous years, making the universe younger than we think. So here the universe is without dark energy is represented by the red and purple lines and blue lines. So red, purple, blue. I know that's not really red, it's pink, but whatever. It decreases for larger values than that of present day density, which means either we're empty or accelerating. But generally, what we're seeing matches this right here. So the cosmic microwave background was discovered by accident by Arno Penzias and Robert Wilson, who were scientists with Bell Telephone. If you're wondering about Bell Telephone, Alexander Graham Bell invented the company Bell Telephone when he invented the telephone. Bell Telephone existed for a long, long time before it was attacked for a monopoly, in which case it broke up, and that's how we got AT&T. So AT&T is what's left of Bell Telephone over here, and then up in the northern Midwest and in Canada, they still do have Bell Telephone Company. Cool things. Anyway, so these scientists were designing an experiment to make America's telephone system better. Part of the project was to get rid of background noise in satellite communications. And while studying the radio wavelengths of the Milky Way, they noticed this bothersome background just hiss, like background static on a radio station. And no matter where they pointed the antenna, it kept coming, never weakening or strengthening, all day, all year. What was determined was that this background hiss was the leftovers of the creation of the universe, which we call the cosmic microwave background. So when these photons, or that are the leftover background noise, were first created, they would have been super energetic gamma ray radiation energy. Super duper energetic. So over time, since the universe expanded, again, remember we talked about the balloon in the beginning where the wavelength would have stretched. It would have redshifted, making them radio wave or microwave spectrum background noise. And since then, the cosmic background spectrum has been measured with great accuracy, giving us stuff like this. So with a more human-centered viewpoint, 7 major phases in the history of the universe have been identified: the particulate, galactic, stellar, planetary, chemical, biological, and cultural evolution. Together, these evolutionary stages make up the grand sweep of the cosmic evolution, the continuous transformation of matter and energy that has led to the appearance of life and civilization on Earth. Were those events random, or were they in some sense natural? This is a huge question that people are asking when they're looking for life. Meaning, were we unique, or is a technological civilization like ours inevitable? Basically, are we one of many, or are we alone? And if that doesn't scare you, I don't know what does. So scientists regard the following as characteristics of living organisms. They can react to their environment. They can heal themselves when damaged. They can grow by taking in nourishment from their surroundings. They can reproduce, passing on their genes. They have the capacity for genetic change and can evolve to adapt to a changing environment. I don't know about you, but that sounds like a couple of things. For example, viruses, which we do not deem living organisms. This can also be looked at as something as in the whole horror story of AIs taking over the world. If they can recreate themselves, pass on information, they can change and adapt. So if you think about it, these rules don't really cover all the options. They don't look at everything. So they aren't one and done. There are other objects that exhibit these characteristics that aren't alive. Another one is stars. They reproduce, they change and evolve to adapt to their changing environment. They can grow, and they do react. They do kind of heal themselves in a way. So we don't really have a good working definition of life yet. However, this hasn't stopped us from trying to find something, because maybe there are distinction, complexity to these rules. Maybe not all life is like us. So extraterrestrial life is summed up in the assumptions of mediocrity, because life on Earth depends on just a few basic molecules. Other things should just depend on these molecules. But because the elements that make up these molecules are all from stars, the laws of science that we know apply to the entire universe. And so given a good amount of time, there must be life elsewhere, right? Well, what do we know about early Earth? So the protoplanet Earth, when stuff started to actually form ground, we don't actually know that much. Geologic record tells us that Earth was once molten, and that there were a lot of impacts, and that we think the combination of these impacts and outgassing from many volcanoes formed our atmosphere and eventually gave us water. So early Earth was home to many shallow oceans. Sea level was much higher at this point as the ice caps hadn't yet formed. Land masses were still forming from volcanoes, and over time, land masses did become more prominent as sea level dropped, and we see land masses like Pangaea forming over and over again. But before our atmosphere really formed, not only were we volcanically active, there was also a lot of UV and radiation bombardments to the planet, because no atmosphere, no protection. It did provide a lot of energy, combined with impacts and natural radioactivity and lightning. This formed ammonia, methane, carbon dioxide, and water that we would need on early Earth with this thinner atmosphere to form amino acids. And nucleotide bases, which is the organic carbon-based molecules seen as the building blocks of life. Amino acids build proteins, which control metabolism. Nucleotides are what make our genes. And so anyway, we have these lovely things, but we aren't really sure how life started from that point. What we do know is that at some point, single-celled organisms formed in the shallow seas, like prokaryotes, which eventually became eukaryotes, bacteria, multi-celled organisms, and eventually we get a stuff like us and dolphins. The smartest thing on the planet, dolphins. How do we try to figure this out? Well, we came up with an experiment that has been reproduced many times, but we've never actually formed life in this aspect. But it's called the primordial soup, or Urey-Miller experiment. It was first conducted in 1953. Harold Urey and Stanley Miller created a mixture of materials thought to be present on Earth long ago, which they dubbed the primordial soup. It's made of water, methane, ammonia, and carbon dioxide. They sparked it with electricity and a few days later checked on the mixture, and they found amino acids like what we had on Earth had formed and nucleotide bases. This demonstrated that biological molecules could be synthesized by non-biological means. More recently, scientists began to ponder, could these amino acids come from outside our planet, like from impacts? Well, why? Because there may not have been a sufficient amount of energy in Earth's young atmosphere to power these chemical reactions, and there may not have been enough materials. So NASA researchers conducted their own version of the Urey-Miller experiment, exposing an icy mix of water, methane, ammonia, carbon monoxide, which is what we found in interstellar grains, to ultraviolet radiation to stimulate energy from a nearby newborn star. They found it formed droplets surrounded by membranes containing complex organic molecules. No amino acids, proteins, or DNA were found, but the results did show that even in the harshness of space, the formation of complex molecules and primitive cellular structure was possible. So the movie Evolution, if you've seen it, if you haven't, please go watch it. It gives good reference for this because in the sci-fi realm, it showed a meteor impacting Earth and then this huge biological explosion occurring, and it was pretty cool. Watch the movie; it's great. Not possible, I think, but totally cool. Anyway, so interstellar molecular clouds are known to contain many complex molecules, and large amounts of organic material were detected on Halley's Comet and the Hale-Bopp Comet. So this means comets may have hit Earth and also have had complex molecules. In addition, a meteorite found in Murchison, Australia, in 1969, soon after it was impacted on Earth, contained 12 of the necessary amino acids to produce life, suggesting that complex molecules for life may in fact form in space. And recent work by a friend of mine, who's Chris Maida and Dr. Pasek, have furthered research on this, stating that meteorites, comets carrying amino acids would only be able to survive in certain atmospheric conditions, meaning amino acid-bearing impacts would not have occurred when scientists may think they had or under the conditions they thought, which is pretty cool. It's actually been a lot of debate. So fossil evidence puts the first one-celled organism, which is algae, at 3.5 billion years ago. Multicellular organisms didn't appear until about 1 billion years ago, and if we put historical perspective into about 46 years rather than 4.6 billion, let's see. Life originated 35 years ago. Earth was about 10. 6 years ago, abundant life flourished. 2 years ago, plants and animals started to dominate the land. Dinosaurs reached their peak about a year ago and then suddenly died 4 months ago. We're still mourning them. Human-like apes became ape-like humans about last week. And the most recent ice age was 4 days ago. It's pretty cold. Homo sapiens emerged 4 hours ago. Agriculture was invented an hour ago, and the Renaissance in modern science occurred in the last 3 minutes. It's been great. Very fast. So as you can see from this analogy, we aren't that significant in our own timescale. Life takes a long time to really get going. So if we've been around for only that much time, but the universe as we know it could be about 14 billion years old, give or take, shouldn't other groups have showed up at this point? So similar events have happened elsewhere in our solar system, right? Like they should have, we think. Well, life as we know it tends to mean carbon-based, because that's what we are. So it's a very Earth-centric view, but it's all we have. What if there were other organisms, like silica-based or sulfur-based? How about other areas in our solar system? We can't rule out life being in more hostile environments like Titan or Europa, but we constantly find organisms living in areas on our own planet that we think is inhabitable, and we call them extremophiles. Last year, or 2 years ago, Netflix came out with a movie about, I think, Titan, and it was kind of a horror movie, and it was about them finding life on Titan that was essentially like this gigantic squid that it was pretty interesting. It's definitely cool. I recommend trying to find it and watching it. But anyway, we have black smokers on the ocean floor, sulfur-rich hot springs of Yellowstone. We find things living there all the time, so why can't something live in Europa or Titan under the ice? So we have yet to find any evidence of life on Mars. No mission was ever sent to the more interesting parts of Mars, though. like the poles, where we expect water existed. Part of that reason is because it was dangerous there, and they didn't want to risk the life of their super duper expensive drone, so they didn't. But if you think about it, that could cause a lot of issues because if you're not sending it to the interesting parts, you can't really expect to find anything. But the most recent mission, which was Mars Phoenix, wasn't equipped to find life. However, it did find evidence of water in the soil near the caps. The chemical composition of the soil there was more Earth-like than scientists expected, and this means Martian microbes may have been capable of digesting oxygen-rich compounds in Martian soil. Fossilized bacteria has also been found recently on meteorites that we have found on Mars. So there is a possibility that maybe there was bacteria on Mars that didn't go too far. I have to eventually check back up on that because, again, it wasn't equipped to find life, but it came back with these samples. So I'm going to have to look back into that. I am also equally as curious as I'm sure you all are as to where that went and if it actually was bacteria, if it wasn't bacteria, was it from Mars or was it from somewhere else? Either way, super exciting. How likely is it that life of any form exists in the universe? We have the Drake equation, which was made by Frank Drake to calculate the number of technologically intelligent civs in the galaxy. I believe he started this during a lunch meeting, kind of like as a well, blah 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 blah, and then it took on a life, and yeah, um, they wrote it on the back of a napkin originally, I think. There are several factors to this equation, and it's largely a matter of opinion, such as are you pessimistic or optimistic? Because we don't have enough information to accurately determine all of them, so we can't really get a nice hard number. But this is essentially it. We're looking at the number of technologically intelligent civs present in the galaxy is equal to the rate of star formation times the fraction of stars having planetary systems times the average number of habitable planets within said system times the fraction of those habitable planets in which life arises times the fraction of those life-bearing planets on which intelligence evolves times the fraction of intelligent life that develops into a technologically advanced society times the average lifetime of said competent civ. What's the rate of star formation? In the galaxy, about 100 billion stars now shine. The estimation is about 10 stars per year. And this may be an overestimate, as astronomers think that fewer stars are forming now than earlier periods, but we're going to stick with 10 per year. Now, the fraction of stars with planets. So, exoplanets is one of the things that we like to do. We like to look for planets outside of our solar system, known as exoplanets. And we've had some success in a way. We haven't exactly found anything like our planet yet, but we found a lot of things like the Jovian planets, and one of the reasons we think we haven't found Terra planets yet is because we don't have the technology for it. Just like we have a lot of trouble finding planets, period. It's been a long process, and we're still working on it, and they're actually coming out with new telescopes that are hopefully going to help with that. But basically, right now, only 10% of surveyed star systems near us have planets. But because of condensation theory, astronomers think it's more likely that all stars have some sort of planetary system. So optimistically, we're going to give a 1 for this value. And then we're going to look at habitable planets. What's the likelihood of a planet being able to harbor life? So temperature is one of the most important factors here. The surface temperature of a planet depends on two things, the thickness of its atmosphere and its distance from its star. So this is a 3D stellar habitable zone of a comfortable temperatures around every star type. So G, F, and M stars, O and B stars would burn out really fast, which are the biggest, brightest stars. So we're going to go with G, F, M. A and F stars have really large habitable zones, so do G, K, and M, but successively smaller. So the habitable zone is the range of distances within a planet of mass and composition similar to Earth that would have a surface temperature between freezing and boiling points of water. So in our habitable zone, we have Venus, Earth, and Mars. Theoretically, if Venus and Mars had actually been switched, they both would be considered habitable and may have harbored life currently, but their conditions are not, and so they don't. But a planet moving on a habitable orbit can still be considered inhabitable. by external events, such as their atmosphere being ripped away, a gigantic crater in the middle, because it got hit by this gigantic asteroid, which may have destroyed everything. Or things like it's too volcanically active, or it's just unstable. Having Jovian planets like ours helps stabilize and protect habitable planets from outside things. And so having a combination is actually good. So then you have a galactic habitable zone. We're getting extensive now. Because there's other forces that can affect it, such as how far are you from the center? So depending on where you are in your galaxy depends on how active it is. So way out here, it's pretty inactive, right? There's not a lot of energy. You're going to have a lot of old or dying stars. Whereas in here, you're going to have this black hole, this very active black hole. You're going to have new stars forming. It's just going to be really active and probably very dangerous for any planets that are there because you'll have star collisions, etc., right? So you kind of want to be in this middle zone, which you have high star density, but it's not too intense in radiation. It's not overly active. It's a nice middle zone. And so this is where you want to be. If you are too close to the radiation, it's detrimental to life. If you're too far away, it's detrimental to life. So the estimated, also like we have an Oort cloud where we have like comets, and we think those comets come towards us because they've been disturbed by other stars. So imagine how much disturbance you would get if it was just like tons of stars, lots of energy, lots of radiation. It wouldn't be good. So only a few % of known planetary systems contain a habitable planet, and potentially habitable moons make this number higher. So with uncertainties, the value of 1/10 for this factor is what we're using for the equation, and 1 potentially habitable planet per 10 planetary systems, being optimistic. So the number of possible combos of atoms is huge because we want to create life. If the reactions that led to life on Earth were random, who knows if it would ever happen again. However, evidence suggests that there are certain chemical combinations that are strongly favored by nature, meaning they aren't random. There's about 1,500 preferred combinations, and they're all made from about 50 simple building blocks. So that means that we're going to give it a value of 1. Evolution of life. The appearance of well-developed brain. Is that unlikely? So one school of thought maintains that given enough time, intelligence is inevitable because natural selection, we tend to go for intelligence, right? Kind of, sort of, maybe. So at least one organism on a planet will always rise up to the level of intelligent life, making the value near to 1. But others, the more pessimistic ones, argue that the only known case of intelligence is us. So for 2.5 billion years, life remained simple and dumb, but it survived. Technically, maybe not. But we were created anyway, and look what we've done. So we're going to be optimistic and go with 1. The 6th factor, estimating if intelligence will inevitably create technology, has led to 2 views. 1, it's not inevitable. It can actually be avoided. So, for example, dolphins. Dolphins are incredibly intelligent, but they don't have tech that we know of. They don't have technology. So that makes the value less than 1. However, there's the other one that not just because we are optimistic opals, but yes, optimistic opals. But because there are many civilizations on Earth independently of each other that created technology, such as the Mayans, Egyptians, Mesopotamians, India, China. So we're going to say that it's probably a factor closer to 1. The final factor, which is the average lifetime of a technology using civilization, is widely unknown. We are the only major planetary civilization that we know of. So we're not really great source material because we're still going. We're still trucking along. How do we figure this out? Instead, we're going to combine the other 6 factors together. So right now, the first 6 factors we've assigned, we've given them a value of 10, 1, 1/10, 1, 1, 1, and 1. And that gives us a value of 1. So therefore, the number of technological intelligent civilizations now present in the Milky Way is equal to the average lifetime of technologically competent civilization in years. Yeah. So that means If a average lifetime of a technologically competent civilization is only 1,000 years, that means there's only 1,000 intelligent civilizations. If it's 1,000,000, that means there's probably 1,000,000. The problem is that if it's a really short time, like 1,000 years, and we are few and far between, I mean, we can't even get to our nearest star neighbor, it would also means communication may never reach each other before we died out. Just kind of amusing. We're gonna assume that maybe, just maybe, there's more than 1,000 or more than 100. We're gonna assume the lifetime of each technological civilization is 1,000,000 years because we're optimistic opals. So 1,000,000 civs, about 30 parsecs or 100 light years from each other, means two-way communication would take about 200 years. And if you look at the last 200 years, we have made a lot of technological advances in leaps and bounds. We have cell phones, for example, and we did not have that 200 years ago. Mm-mm. Let's see, we're in the 2000s. 200 years ago, we were just getting the light bulb. Yeah, imagine talking over that period of time. We'd be like, hey, dude, I just figured out the light bulb. What did you do? 200 years. Oh, we figured that out ages ago. We just figured out interstellar travel. 200, 400 years have now gone by. Oh yeah, us too. Them. We've already colonized half the universe. 200 years. It's impractical. And travel could be even more impractical because it could take about 1,000,000 years for us to get there, in which case they'd be dead. And that's with our current level of technology. All of this is just not very pragmatic. So our own search is possible. If we did launch probes, for example, the Pioneer 10 in 1972 and Voyager in 1978, to which we attached data about our own civilization, mostly in the universal language of math. I don't know how many of you like math, but I would not like that if I was the alien that found this probe. I'd be like, wow, who wrote in math? Like, what is wrong with you people? But generally, we assume that it's the universal language. Voyager, we had attached additional things like sound stuff, and it's constantly talking about us. But either way, Pioneer 10 has finally made it well beyond Pluto and is on our way out of our solar system at this point. So it's been a while. So despite having probes out there in search of a life, we have no way of finding out if they've been found because there's no way for communications back. That means that thing or group of things that found it would have to find us, which can be problematic. Think about it. Worst case scenario, they're going to kill us all and colonize us or sell us for slaves. Woo! So a much more practical way of communicating is using electromagnetic radiation, like radio waves. So radio wave bands don't get impeded by dust or gas or other material in space, making it ideal to communicate with. And because we possibly can't broadcast to all the stars, what we do instead is listen. We listen for communications from other civilizations, but this has raised a couple questions. Which direction do we point our radio telescopes? Are other civilizations even transmitting communications on the wave bands that we are listening to? And if they are, how do we know it's them and not something that forms naturally in space? So think about Earth. We give off a lot of radio waves. At this point, we give off more than the sun. Spinning Earth would emit bright flashes of radio radiation every few hours as the most technological regions of our planet rise and set. Any sufficiently advanced civilization that resides within 70 light years from us would have noticed us by now. But it is very plausible, like Bill Nye has pointed out, that the other civilizations may not be communicating on the radio spectra. Why, you may ask? Because they may have figured out advanced communications on other wavelengths, basically saying they have fiber optics and we are still using copper wire. So the other thing is that because of finding these advanced forms of communication, that all radio emission ceases, and that it's a lack thereof that indicates intelligence. We just aren't intelligent yet. Assume other civilizations do in fact communicate using radio waves. What frequency would they be on? Some arguments suggest that civs might communicate at wavelengths around 20 centimeters in length. Okay, so that means between the height and the height, 20 centimeters. That's a long So hydrogen atoms give off the 21 centimeter wavelength, and hydroxyl, or OH, hydroxyl acid, the molecule OH, also radiates near 18 centimeters, and together the OH and H wavelengths, well, they form H and HO make water, right? H2O. So since water is arguably, from what we understand, the major evolution medium for all life, radio radiation travels through the disk of our galaxy with the least disruption at these wavelengths, 18 and 21. So researchers have ordained the 18 to 21 centimeter wavelength range the best wavelength range for communications. And since OH and H make water, it has been dubbed the name the watering hole. Because this radio interval may serve as an oasis where all galactic civilizations would gather to conduct their electromagnetic business. This sounds like something out of Andromeda or any other TV show that takes place in space, like seriously, that you would find on the Sci-Fi Channel. Like, I'm not even kidding. This sounds right after science fiction, but it's the only thing we got, and it may be plausible because people are funding this. So the 18 to 21 centimeter range also lies in the quietest part of the spectrum, where we are receiving the least galactic background noise, or static, if you want to think about it that way, from interstellar clouds. Atmospheres of typical planets also interfere less at these wavelengths. A few radio searches are in progress at frequencies at and around the water hole. One of the most sensitive projects for the search for galactic sieves is the SETI Institute, which is the Search for Extraterrestrial Intelligence, or SETI. They have a nice telescope array out listening. You can go to their website. They have a lot of information up there. It is a really cool institute. And their whole spiel is that they are looking for extraterrestrials, and they are actual serious scientists. So it's not like some dude hanging out with tinfoil on his head going, "They're coming, we're all doomed." But seriously, check out their website. SETI is pretty cool. So why haven't we found or seen any signs of life? There should be something, right? So this is where we have the Fermi Paradox. We haven't seen anyone yet, but supposedly there should be many, many intelligent life forms in the galaxy. The Milky Way contains hundreds of billions of stars, and billions of them are similar to our sun. So it is highly likely that some of these stars will have planets that are similar to Earth. So if we assume via the Copernican principle that Earth is not particularly special, then intelligent life should exist in some fraction on these Earth-like planets. Some of these intelligent life forms might develop advanced technology like interstellar travel. We haven't got there yet, but if you look at Star Trek, we didn't get there. It was the Vulcans who helped us with that. So maybe they're out there waiting. But some of these intelligent life forms might develop this on their own. Hopefully we'll get there one day without help from the Vulcans. But interstellar travel would take a long time. But as there are many sun-like stars that are billions of years older than us, there has been plenty of time for such travel to have occurred. So given all of this, why have we not seen anything, or anyone, or heard a peep? Where is everyone? So the SETI Institute is actually dedicated entirely in looking for signs of life outside our solar system. They haven't heard or seen anything yet, which has led to the creation of the Kardeshev Scale, where we have 3 types of civilization: Type 1, Type 2, and Type 3. Type 1 civilization has the ability to use all the energy on their planet. We are not quite there. We are at Type 0.7, which was created by equation by Carl Sagan. And then there's Type 2, which can harness the energy of their host star. Type 3 blows the other 2 away, accessing power comparable to that of the entire Milky Way galaxy. We are barely 1. But why haven't we seen any other life? Our biggest reasoning right now is something that has been come up with where we call it the Great Filter. Which basically what we're saying is there isn't any other higher life forms. The idea is that a planet with a civilization would need to get to Type 3 in order to do intergalactic travel. So maybe there aren't any yet. Maybe we are the first species to kind of start. Maybe other ones have died off. Maybe they're just, again, not there yet. So what is the Great Filter? Essentially, it's a whole bunch of hurdles that every civilization must overcome in order to proceed. So this means either we have passed the hurdle and yay! We still have to pass said major hurdle and we are screwed. We are the first civ to actually make it past the hurdle, or other civilizations made it and then killed themselves off before we could meet them. Another theory is that there is intelligent life beyond our own, but they have yet to interact with us. Star Trek is a great example. Like I said earlier, the Vulcans watched humans on Earth, and they reached out once we reached a specific tech advancement, and then they gave us what we needed to travel the galaxy. But other options may be that they are zookeepers. We're actually being observed for anthropological reasons. They're staying away because the oxygen we breathe oxidizes us, and so to outsiders, we are fire breathers. Do not mess with the death breathers. We are breathing fire. We're too primitive. We can't pick up their signals yet, so they're ignoring us. We live in the sticks. Nobody comes out here. Colonization is hysterical to higher civilizations, and they just kind of stay on their own planet or just go off looking for whatever, science. There's a predatory civilization that is out there killing off others. Therefore, we are being stupid. Another civilization did visit here, but before we formed, so we missed them. Or, like Jupiter ascending, we're actually food for another species, and we just don't know it. So these are both about the Fermi Paradox, part 1 and 2, where we're talking about where the aliens are and all the different options. And it basically helped explain everything I just said. So I hope you watched them. I hope you enjoyed them. And that was our last lecture. Again, if you have any questions, post them. And I hope you have a great day. Bye!